Today we're going to be learning about dynamic equilibrium. This is quite a strange feature, so it needs some explaining. If we break it down into two words, we have equilibrium, which would mean everything's equal, and yet dynamic would suggest movement. So it suggests that although everything's equal, things are moving. And the best way to consider that is to imagine running on a treadmill. So you've seen people at gyms running along for miles and miles and miles, and yet they never appear to move anywhere, because on their machine, as they're running along, the treadmill is moving in one direction as they're running in the other. So the equal part is their position, because their position stays the same, and yet they have, because of the treadmill, moved. And that's a great example of dynamic equilibrium. Things appear to be equal, and yet there's lots of movement occurring. Now in science, this most often occurs when we see something called a reversible reaction. The most common one of which is called the Haber process, and it is the method of production of ammonia. But in an example of a reversible reaction, we have our reactants, perhaps A plus B, in a reaction, followed by this symbol, and then this might join together to make the compound AB. The symbol here is suggesting that there is movement in one direction, forwards, but there is also movement in the opposite direction, backwards, i.e. reverse. And that's what makes this a reversible reaction. Now, to explain further, this means that A and B are reacting, and they're reacting to form AB, but as they react to form AB, AB is just chemically breaking down to form A plus B again. So, in other words, we have A plus B making AB, but at the same time AB is reacting to make A plus B. This means that we have a reversible reaction. It's going round in a cycle. So that gives us reversible, that's fine. But that's our dynamism. We have things constantly breaking down and being remade. So what makes it a dynamic equilibrium? Well, the fact is that as this reaction is happening, at some point you're going to end up with a relatively constant amount of AB, because it's always being made, and a constant amount of A plus B, because it's always breaking down. And at that point it may be something like, if I put this down here, A plus B and AB, that in a mixture there might be 50% of the chemical is in the form of AB and 50% is in the form of AB together. So that seems fine. We've got this mixture. How does that still make it dynamic though? Because we've got 50% here and 50% here. Well, the fact is, although it looks like this value is constant, the actual individual molecules and atoms that are making up this AB and this A plus B are actually changing all the time. So some of this, in any one instance, I will see maybe atom A and atom B as being separate, and then we've got separate atoms here that are joined up as AB, whereas if I come back in 10 minutes' time, it might be that atom A and atom B have now combined and over this side of the equation, whereas the A and B that we had here have now broken down and gone over to this side. I sometimes view this as being like students with girlfriends and boyfriends in the year 11. So in my class, I may have maybe 2 or 3 students that have boyfriends or girlfriends at the start of the year. And at the end of the year, I might still have 2 or 3 students that are in relationships. However, it's not the same students. So although the proportion of students in a relationship has stayed the same, the actual students that are in that relationship has changed. So we have the constant proportions, which makes it the equilibrium, but it is changing the individuals, which makes it dynamic. That is the dynamic equilibrium. Now, our really common example that we see, which is the Haber process, is the process by which we get ammonia from air to make ammonia for fertilizers. And in that case, we have nitrogen as a gas plus hydrogen as a gas, and that makes ammonia as a molecule, or a compound in a molecule. Now, the thing with this is that as you're making the ammonia is also constantly breaking down. Now, in this case, the dynamic equilibrium means that maybe something like 95% of the reactants are separate as the nitrogen and the hydrogen, and only 5% is present as the ammonia. And what we do is we collect that ammonia and we remove it. The proportions here, though, can be changed. We can change the conditions in the reaction to try and encourage the forward reaction to be greater than the reverse reaction. And if we can do that, we can encourage this percentage to increase to maybe 15% and this to decrease to maybe 85%, and therefore we make this reaction much more profitable for us as chemists. So the proportions here depend on the conditions that we apply to the reaction. So that is reversible reactions. In summary, dynamic equilibrium. In summary, dynamic equilibrium is where we appear to have equal proportions in reversible reactions, and yet the actual reactants and products are constantly changing. And our most common example of that we find in the Haber process, where we have nitrogen and hydrogen being used up to make ammonia, but that ammonia is constantly breaking down to form nitrogen and hydrogen again.